young seminar series. Today we have two speakers, Altieri and Matteo Bognino. And we start with Ada, and I will just say a few words about her career, and then we will have the presentation of the seminar. Ada Altieri obtained her PhD in theoretical physics from both University of Rome La Sapienza and University Paris Sud 11, co-advised by Giorgio Parisi and Silvio Franz. During her PhD, she focused on the renormalization group techniques in the disorder system and on the connection between constraint satisfaction problems and the jamming transition in high dimension. Starting from November 2017, she finished her PhD and she obtained a postdoctoral fellowship at Laboratoire de Physique Théorique at the École Normale Supérieure in Paris, in collaboration with Francesco Zamponi. And 1 year later, she joined the team of Giulio Piroli, working with the International Simons collaboration on cracking the glass problem. In 2020, she was awarded the L'Oréal UNESCO Fellowship for Women in Science for her research on the ecosystem complexity through the prism of statistical physics. And since December 2020, she is assistant professor at the Laboratoire Matière des Systèmes complexes of the University of Paris. So please, Ada.
Okay, thank you. Thank you for this introduction, and thank you first of all for this invitation. It's a great pleasure for me to talk today. And today I would like to discuss this work, evidence of glassy phases in large interactive ecosystem with and without demographic noise, which is essentially based on these two papers. The first one with Silvio Franz and the second one that has been recently posted in archive in fall 2020. And so over the past 7 years, let's say, I have been working on different subjects related to disorder systems, in particular spin glasses and glassy system, with a special emphasis on a class of constraint satisfaction problems with continuous variables that has been recently shown to fall in the same universality class as jamming transition, which is a rigidity transition that takes place at t equals 0 inside the glassy phase. And then in the last 3 years, I moved to slightly different subjects. There are, on one hand, dynamical mean field theory approach to achieve a better understanding of aging dynamics in disorder system and deep neural networks, and on the other hand, on theoretical ecology. And so one of the main purposes of today's talk is basically to show that all these apparently different fields are not so far away one from the other, but can be essentially connected and share a dense network of connection. And in particular, I want to stress a one-to-one correspondence between spin glasses and glassy system in the low temperature phase and critical ecosystem that seem to be posed at the edge of stability. So in the following, I will focus on these two reference models in theoretical ecology with a special emphasis on the second one, so on the Lotka-Volterra model in high dimension with random symmetric interactions. And so understanding mechanisms that shape the diversity, stability, and functioning in ecological and biological community is a very timely problem, but at the same time a challenging problem. And there are still a lot of open questions in theoretical ecology, ranging on how does the diversity affect the evolution of the other species? What about cooperative patterns? Are these patterns ordered, disordered? How does an ecosystem respond to an external perturbation? And is it possible to quantify, to characterize this response function in a similar way as we do for physical systems? And again, is it possible to detect a multiple equilibrium regime or even more complex chaotic dynamics? So the field of theoretical ecology has gathered momentum in recent years, trying to answer for this challenging question, but also fostered by an explosion of experimental result and increasingly sophisticated techniques. However, the true novelty now compared to studies carried out in the last decades is that theoretical ecologists and physicists as well are no longer focusing on ecosystem formed by a few species, but on ecosystem formed by many, many species. And so in this particular limit, in this particular regime, we can take advantage of statistical mechanics tools and statistical mechanics of disorder systems to provide an effective mean-field description and characterize emergent mechanisms and collective behaviors in terms of phase transition. And so here I reported a few works for the sake of compactness, starting with Solé, Alonso, and McCain in 2002, and going on with Kessler and Streb in 2015. But I also want to mention this work by Tikhonov and Monasson dating back to 2017, that is essentially a reformulation of the MacArthur model in high dimension that with Silvio Franz we rephrase it as a constraint satisfaction problem, and specifically a perceptron model, to show that constraint satisfiability can provide an alternative mechanism, a complementary mechanism to self-organizing criticality, self-organizing instability, edge of chaos, to explain criticality in large ecosystems. However, today I would like to touch upon another problem in theoretical ecology, in particular to touch upon another canonical model of disorder ecosystems, that is the random Lotka-Volterra model, that has been recently shown in this paper to be a good platform able to capture the most relevant features from various community models that include cascade prediction, resource consumers models as well, and plant pollinator, by essentially tuning 4 control parameters. And so the starting point of this Lotka-Volterra model is the dynamical equation for the relative species abundances Ni, where I is an index that runs from 1 to S, where S is the total number of species in the species pool. And so the dynamical equation, the Langevin equation for this model can be written in this way, where the first term is the self-regulation term, so it can be written as a gradient with respect to Ni of this one species potential, that in the Lotka-Volterra model is assumed to be quadratic in the species abundances Ni. And as I said, is a self-regulation term in the sense that if one species experiences overcrowding in the immediate environment, it will be pushed back to its own value of the carrying capacity Ki, which is a stable fixed point of this system. Then we have this other part, which is the interaction part of this model, where this alpha j can be tuned and can be changed to pass essentially from a mutualistic regime to a highly competitive regime. And then to add the source of stochasticity, we add this noise, Eta, which is assumed to be Gaussian, so with zero mean and covariance given by this expression. So as you can see, the covariance of this noise is proportional to T, which plays exactly the same role as a physical temperature. So this T is the amplitude of this noise, which is a demographic noise accounting for death, birth, and other unpredictable interaction events. And so as you can see, it's also proportional to this Ni, the relative abundances. And then we had another term, which is this immigration parameter lambda, that at the first level analysis is assumed to be species independent. So the basic assumption to get an exactly solvable model is to start from a well-mixed community, so no space dependence, treat this noise within the Ito formalism that allow us to essentially to attain an exactly solvable model by starting from the assumption that Ni and Eta I are uncorrelated at the same time. And then the most relevant assumption is that to tackle the staggering complexity of the ecosystem, we assume these alpha j to be random variables, extracted from a given distribution, which is parameterized by the first 2 moments, basically the mean, mu over S of this matrix alpha j, and the variance, sigma squared over S. And so in this way, we are essentially following Robert May, who was a pioneer in this field, who first studied stability and complexity of ecosystem by using random matrix theory techniques. And so one special case in this model is to assume symmetric interaction, so alpha ij equal to alpha ji. And in this particular case, with the random symmetric interactions, the dynamical equation that I showed before admits an invariant probability distribution, P of Ni, which is written as the exponential of minus beta h, where this h, these Hamiltonian operators, takes this form. So it has a quadratic part that exactly came out from the quadratic one-species potential for the Lotka-Volterra model, an interaction part that depends on this alpha ij, and then two other terms that come into play when we do the mapping between the dynamics and the static formalism by passing through a Fokker-Planck approach. And so this demographic noise is modeled as T log of Ni, and this other term is specifically introduced to model this immigration parameter. So what is the problem? The probability distribution of Ni is well defined and well regularized, but the effective potential for this model has a well-defined form just when lambda over T is greater than 1. Otherwise, we get a nasty regime where lambda over T is much smaller than 1, and so to prevent all the one species to get extremely close to the boundary that correspond to the I equals 0, we need to resort to some particular strategy. And so one possible strategy to prevent species from getting very, very close to 0 is to impose an hardcore, a reflecting wall that correspond formally to this theta function, to this Heaviside function. So the Heaviside function essentially means that when Ni is greater than lambda, the Heaviside function is 1, and so the log of 1 is 0, and this term does not matter. Whereas when Ni is smaller than lambda, this theta function is 0, and so the log of 0 is minus infinity, that with a negative sign provide a reflecting and hardcore repulsive boundary. So as you can see, for people who are familiar with disorder and system and spin glass system, without these last two terms, so without the demographic noise and the reflecting wall, essentially this Hamiltonian operator reminds you a spin glass Hamiltonian, where basically a Sherrington-Kirkpatrick Hamiltonian or a p-spin with p equal 2, where you have a quadratic potential, a quadratic one spin, one species potential, and an interaction part that depends on this alpha ij. So this model without demographic noise and without reflecting wall, basically at 0 temperature, was studied in 2017 by Guy Bunin and then rephrased within the Replicon method by Biroli and collaborators in 2018. And so the author established this phase diagram for sigma, which is the heterogeneity parameter, as a function of the mean interaction mu. And so as you can see, for small interaction or highly homogeneous interaction, the system is in a single equilibrium phase. Then you can pretend to increase this parameter sigma, and what happens? The stability decreases and the diversity as well decreases, and the system enters this multiply equilibria phase. However, the authors did not enter into many details of this multiply equilibria phase, and then one can wonder what happens here. So what are the properties of these equilibria? Are they stable? Are they unstable? Are they marginally stable? And how many equilibria are there? Are they exponential into the system size? Are they sub-exponential? So to better investigate the properties of this multiply equilibria, this more structured phase, what we can do is, for instance, to introduce, re-plug into the model the demographic noise, and in particular to study the effect of this interplay between the demographic noise and the migration parameter. And so one possible strategy to deal with the to perform a thermodynamic analysis is to resort to the replica method, which is a well-known technique in disordered system that allows us to write the disordered free energy in terms of the log of this disordered partition function. And so thanks to the replica trick, we just need to compute a log of the average of this replicated partition function and eventually take the analytical continuation for n going to 0, where n is the index used to introduce the number of replicas into the systems. into the system. And then we have to compute this log of this quantity average over these random variables alpha ij with mean mu over s and variance sigma squared over s. And so according to this definition, to properly deal with this disorder average, we need to introduce two order parameters that are basically the overlap matrix, so the degree of similarity between these two copies of the same system, and HA, which in spin system is a sort of magnetization, and here is specifically the average abundance. And so according to this definition, we can rephrase, we can rewrite this disorder free energy in this way, which is now an integral over the overlap matrix and this other order parameter HA. And since we are interested in the thermodynamic limit, so when S is going to infinity, we can basically take advantage of a saddle point approximation and evaluate this action by extremizing the action with respect to the order parameter and finding the stationary condition, the stationary value for this overlap matrix and this other order parameter HA. So the simplest scenarios in this approach is what is called the replica symmetric ansatz, according to which this n times n overlap matrix is just parameterized by two values, one of the diagonal, which is QD, and another one on the off diagonal, Q0. And for H, we just assume a uniformity condition, so HA is equal to H for every A. And so basically what we can claim is that this replica symmetric ansatz is feasible, is perfectly fine when we are in the high temperature phase, because the landscape is well captured by these ansatz. But upon decreasing the temperature, this ansatz becomes unfeasible, becomes invalid, because it's no longer able to capture the increasing complexity of the landscape. And so in the low temperature regime, we should resort to a one-step replica symmetry breaking ansatz, according to which this n times n matrix is now divided in n over n boxes, and each of these boxes contains m replicas. So basically, rephrasing these matrix structures in terms of the landscape, we have now two different overlaps. Q0, which is the size of the largest basin, and Q1, which is the size of the innermost and deepest basin in this two-level structure. And so as you can see, since Q1 is greater than Q0, basically larger overlaps are associated to smallest and deepest basin of attraction. And so given these mathematical details, given these mathematical premises, what we can see in terms of the phase diagram of the Lotka-Volterra model. So as I said, this phase diagram was represented at zero temperature by Bunin and collaborators in 2017, but now we can pretend to add another dimension to the problem, and in particular to add the temperature to this model. And so I imagine here to have another axis, which is a physical temperature, and what I notice is that there is no sensitive dependence on the average interaction parameter mu. So basically I can just focus on a two-dimensional plane, on a two-dimensional phase diagram, which plots the amplitude of the demographic noise as a function of sigma, the heterogeneity parameter. And so I can basically reinterpret emergent collective behaviors in terms of disordered phase transition. And so at very high demographic noise, when the noise is sufficiently high to cover random interaction, the system is in a single equilibrium phase, and so the landscape is purely convex. Then, upon decreasing the amplitude of this noise, the system approaches this blue line, which is the stability line of this single equilibrium phase, and enters this multiply equilibria phase, which is formally characterized by a 1-RSB ansatz. And going deeper and deeper in T, the system crosses this other line, this orange line, which represents the stability line of this multiply equilibria phase, and the system enters this Gardner phase that I'm going to characterize into more detail in a while. So how do we get this particular phase diagram? Essentially by looking at the harmonic fluctuation of the free energy at finite temperature up to zero temperature. And so what we need to do is basically to compute the stability matrix, so the matrix of the second derivative of this action, with respect to the overlap matrix QAB and QCD. And so this stability matrix embeds a first diagonal term and another part, an off-diagonal part, that can be written as an average over the thermal measure and the disorder of this 4-point connected correlation function. And this matrix has to be properly diagonalized on a proper subspace, and we need to look in particular the leading eigenvalue of this matrix that provides the stability criterion for each of these space. So this is particularly the expression of what is called the Replicon Eigenvalue, which provides a first signature of a criticality, of a critical transition, because when this a vanishing behavior of these Replicon eigenvalues is a signature of an emergent transition. And so it basically corresponds to this blue line in the phase diagram. But this stability criterion can be generalized in particular to get this other orange line, which corresponds to the instability criterion for the multiply equilibria phase, and so the appearance of a more structured Gardner phase. So to recap the main properties of this phase diagram, as I said, I highlighted no sensitive dependence on the average interaction parameter. And so I could just focus on the two-dimensional phase diagram for T as a function of sigma. And now I want to enter into more detail of this intermediate phase, this multiply equilibria phase, because we also perform a complexity computation or configurational entropy computation in accordance, in agreement with Monasson computation. And essentially we have to compute the average of the log of the number of equilibria at a given free energy density divided by 1 over S, where I remind you that S is the number of species. And what I discover is that this complexity is strictly positive. So basically meaning that the number of equilibria in this intermediate phase is exponential into the system size, is exponential into the number of species. This quantitative outcome is particularly timely also in light of stability landscape and ecological resilience concept, and notably is particularly timely in relation with recent findings in microbial community that try to explain this appearance of multiple stable equilibria in real ecosystems. And so the other remarkable features that appears from this phase diagram is that at very low demographic noise, a marginally stable amorphous phase can be detected. And so what does it mean? So essentially each of these basins, each of these equilibria splits into many subbasins according to a hierarchical, a fractal structure. And so it becomes now a metabasin according to a hierarchical organization of these equilibria, and in close analogy with spin glasses and glassy system. And so we also perform with Silvio Franz's previous studies in this direction, in particular in the high-dimensional MacArthur model, but we didn't find there any signature, any evidence of a symmetry breaking effect and the appearance of a Gardner phase. So this is basically the first evidence in these concepts of this Gardner phase that is particularly relevant in glassy system. And so to better understand these properties, I want to focus on the properties of the landscape in a glassy system. We can, for instance, consider a system of our sphere or soft sphere in infinite dimension, where the control parameter of the model, depending on whether we are looking at soft sphere of our sphere, is the temperature or the density of the system. So in this particular case, we focus on a system of our sphere in infinite dimension. And so the control parameter is now the density. So depending on this control parameter, we can be in a liquid phase where the phase space is completely ergodic and the dynamics at long time is purely diffusive. Then upon increasing the density or decreasing the temperature, we can enter another phase, which is called a normal glass phase, where basically this phase space splits, shatters into many clusters. And so the size of this cluster is essentially proportional to the amplitude of vibration inside each cage where particles are confined. And then upon further decreasing the temperature or increasing the density, the system can enter another phase that it was discovered, that it was pointed out in 2014 in glassy system, which is called Gardner phase, which basically signals the appearance of a marginal glassy phase, where each of these basins splits into many sub-basins according to a hierarchical structure. And so accordingly, basically also vibration in real space are very, very heterogeneous. So there are regions of the real space that are highly vibrating and other regions that are roughly frozen. And so given these premises, given these properties in terms of the landscape, what we can claim in terms of the dynamics. And so to address this question, to address this problem, we also looked at the dynamical correlation. And in particular, we defined this dynamical correlation function, and we studied it in detail in the single equilibrium phase and the multiple equilibria phase. And so what we show is that in the single equilibrium phase, this dynamical correlation is not function of two separate time t and t prime, it's just function of a single time scale, t minus t prime. And so in the single equilibrium phase that I also call the replica symmetric phase, the dynamics is time translational invariant, and as you can see from this plot for the correlation as a function of time obtained for different t prime, basically all the curves collapses at the same value, which is Q0, the theoretical predicted value within the replica symmetric ansatz. And what happens in the multiple equilibria phase? Well, in the multiple equilibria phase, the system never settled down in any of these equilibria, but start to explore the basin of attraction of the most numerous and marginally stable equilibria, revealing an aging dynamics exactly as it happens in mean-field spin glass system. And here I want also to compare these thermodynamic quantity that are H, QD, and Q0 to the corresponding quantity in the dynamics that are basically an average population and the short time and the long time limits of the correlation function. And so as you can see from this plot, there is a remarkable agreement between theory in orange and numerics in blue with the error bars up to this dashed orange line, where this dashed orange line corresponds to T1 RSB, where ergodicity breaking effect starts to appear and the dynamics is no longer time translational invariant. Then, for the last few minutes, I want to discuss other application of these Lotka-Volterra models in close related contexts, because the study of these phases, and in particular of the dynamics of the Lotka-Volterra model, reveals wide-ranging application in many different contexts and in very different fields that include also models for population genetics, the analysis of niche equilibrium, as well as a deeper study of evolutionary game theory. And so here I want basically to establish a direct mapping between this Hamiltonian, which is the Hamiltonian of the Lotka-Volterra model without demographic noise and without immigration, with the Hamiltonian of what is called the random replicant model. So the random replicant model basically describes an ensemble of n replicants that evolve according to random interaction. And so now the random interaction are these JAJ that at variance with this alpha ij have zero mean and variance j squared over s. But provided a proper rescaling of the control parameter of the model, we can have exactly we can have a one-to-one correspondence between these two Hamiltonian and in particular between these two models. And I recap here the mapping between this Hamiltonian in the Lotka-Volterra model without demographic noise and this random replicant model. So as you can see here, this parameter A that multiply a globally quadratic constraints can be put in correspondence with this sigma parameter, this heterogeneity parameter. And this gamma, which is introduced because of this additionally constraint in the random replicant model that enforce the total concentration to be equal to S, is essentially in correspondence with this move, with this average interaction. But as you can see from the phase diagram for T, for the temperature as a function of sigma, there is no strong difference, no qualitative difference. We still recognize three different phases: a single equilibrium phase, a multiple equilibrium regime where the equilibria are exponential into the system size and stable, and the Gardner phase, which is properly characterized by a full RSB ansatz. And so, given these details, so one can wonder, how do we expect this phase diagram to change when we introduce a small degree of asymmetry? Well, we do not expect these two phases to change, because basically here the equilibria are stable, so this is just a purely convex landscape, and here the equilibria are stable as well. So we should expect instead that this Gardner phase is completely washed out, completely wiped out by introducing a small degree of asymmetry. And if we introduce, if we don't consider demographic noise, in particular, this phase should be replaced by an exponential number of chaotic attractors. But if we consider the demographic noise, we can claim that these two phases remains completely unchanged, and the only phase that disappears is basically this one, which is because of the properties of the marginally stable equilibria here. And now I want to come to my conclusion. So in this talk, I basically discuss a Lotka-Volterra model in high dimension with random symmetric interaction and in presence of a finite demographic noise. And I highlighted two different multiple equilibria phase, a multiple equilibria phase, which is characterized by an exponential number of stable equilibria by combining thermodynamics and the dynamical mean theory formalism, and the Gardner phase, where the equilibria appear to be marginally stable, and that is akin to what appears, what takes place in the jamming of amorphous solids. And then for the future, what I would like to do is to go behind the well-mixed community assumption, and so to introduce a notion of space that can result in non-trivial patterns, including activity front, traveling waves, and spiral structure. And I would like also to better investigate what happens to this phase diagram with stronger and stronger interaction that can result in periodic cycles or even intermittent dynamics. And so this is the end of my talk, and I would like to thank you for your attention.
Thank you, Ada, for the talk. Are there questions or comments?
Have a question.
Yes, please.
Hi, Ada. Nice talk, thanks. Just a quick question. Is the transition from the replica symmetric to the 1RSB phase continuous or discontinuous?
It's a continuous transition.
Okay, so the complexity starts from 0 and then...
exactly.
And then the...
Yes.
Okay.
Yes.
Thanks.
Thanks for the question.
Questions or comments? I have one question. You started your talk by saying that there are, let's say, a lot of new methods to monitor ecological systems, right? So is there any of these ecological system that may fit one of your models? Or this empirical one, I mean.
Empirical system that fits my model? Yeah, there are a lot of experiments in this direction. For instance, there are experimental study of microbial population that can bring power to this theoretical prediction. And for instance, why microbial population? Because through microbes, we can have access to long evolutionary timescales, and also microbial growth can be studied in vitro under well-controlled condition, well-controlled situation. And so, for instance, we can look at, we can reproduce a chemostat in which we vary the influx of nutrients and the availability of resources to the different species. And so changing the number of nutrients is basically the same as changing the heterogeneity of the interaction. So there are several studies in this direction, for instance, by the group of Jeff Gore who look at this kind of models of microbial community or studies on the gut microbiome. And so if you change the number of nutrients, you are basically changing the interaction, the strength of the interaction. And so in this particular regime, we should expect a multi-stability phase or something like that. So a multiple, the appearance of multiple steady states should be more likely.
Okay, thank you. Other questions or comments? So if not, let's thank again Ada.